So we've finished all the main topics in Galilean relativity. Now I'm going to talk about some of the problems that Galilean relativity has, and this will set the stage for why we need special relativity. First, I'll give a brief review of Galilean relativity, then I'll discuss some of the problems with it. In previous videos, I said that the main goal of Galilean relativity is to calculate all the different quantities that we disagree on in different inertial reference frames. The most important of these was position, but it also includes velocity, momentum, and kinetic energy. We've seen that in Galilean relativity, observers in different reference frames will agree on time, but they will disagree on position. We showed that we can convert between the space-time coordinates of the man and the car using the Galilean transform equations, where v in this case is the speed of the car measured from the man's reference frame. In this example, the car's speed is 1/2 because the world line runs 1/2 unit of position for every upward rise of 1 unit in time. Because time is universal in Galilean relativity, instead of writing t car or t man, I'm just going to write the letter t. And using the Galilean transform equations, we know how to convert the position coordinate for the man for any event in spacetime to the position coordinate for the car. If we know a little bit of calculus, we can immediately use this equation to convert between velocities in the reference frame of the man and the reference frame of the car. All we have to do is take the derivative of both sides with respect to time. So the velocity of an object in the car's reference frame is dx tilde car by dt. And this equals the velocity of that same object in the man's reference frame, dx man by dt, but also subtracting the derivative of v times t. And this derivative is just the constant v, which is the velocity of the car measured from the frame of reference of the man. So, given the Galilean transform equations, which are used to convert between time and space in different inertial frames, we can easily get another formula for converting velocities in different frames. And from there, it's easy to get formulas for momentum in different reference frames, since momentum is just mass times velocity. And the same can be said for kinetic energy, which is just 1/2 times mass times velocity squared. So the most difficult thing to do in Galilean relativity is calculate the position in different reference frames. And from there, calculating velocities, momentum, and kinetic energy is very easy. But what about the things that we agree on? In Galilean relativity, we agree on time, the spatial separation between objects, and mass. But most importantly, we agree on the laws of motion in different reference frames. In other words, the laws of motion, like Newton's second law and Newton's law of gravity, should be invariant in different inertial reference frames. Remember, invariance is the idea that the same object can look different in different reference frames. We've already seen invariance when it comes to geometry. We've already seen that the same vector r can have different components in different coordinate systems. But now let's consider physics in Galilean relativity. We would now like to show that the force acting on an object is invariant and is the same in all inertial coordinate systems. So we know that Newton's second law says that force equals mass times acceleration, assuming that the mass is constant. In other words, force equals mass times the second derivative of position x with respect to time. Now let's try changing coordinates by adding a constant term k to the position, which basically just shifts the origin of the coordinates. After taking two time derivatives, the constant k goes to 0, and we see that Newton's second law, F equals ma, still holds. Next, let's try adding a linear term, velocity multiplied by time. This is basically just doing a Galilean transformation on our coordinates, moving to another reference frame with a constant speed v. Again, after taking two time derivatives, the linear term goes to 0, and F equals ma still holds. Now let's try adding a second order term to the position, 1/2 alpha t squared. This is like changing coordinates to an accelerating reference frame, like a car that's speeding up. After taking two time derivatives, the constant alpha survives. So in an accelerating reference frame, Newton's second law, F equals ma, does not hold true. Because we're in a non-inertial frame, we end up with an extra fictitious force, which makes Newton's second law no longer valid. This extra fictitious force is why you feel your body being pulled downward in an elevator that's accelerating upward, or why you feel thrown back into your seat in a car that's accelerating forward. So, Galilean relativity is the idea that the laws of motion are the same in all inertial reference frames, and this idea is compatible with Newton's second law. We've shown that force vectors in Newton's second law are invariant. They're the same in all inertial coordinate systems. Observers in different inertial reference frames will all agree on the same invariant force vector. Now we would like to figure out if the laws of electricity and magnetism are also invariant. In other words, is the force vector due to electricity and magnetism the same in all inertial reference frames when we use Galilean relativity? Well, the short answer is that the laws of electromagnetism are not invariant under the Galilean transform. And the ultimate reason for this is that the speed of light is invariant in all reference frames. And taking this idea into account leads us to special relativity, which fixes the problems with electromagnetism and the Galilean transform. But first I'll explain why the Galilean transform fails in electromagnetism. You may have seen the four Maxwell's equations, which describe the behavior of electric fields and magnetic fields. If you've studied vector calculus, you should be able to understand the behavior of electric and magnetic fields in terms of the gradient, divergence, and curl operators. However, even if you haven't studied these concepts, I'm hoping you'll still be able to follow my line of reasoning for why electricity and magnetism is not compatible with the Galilean transform. In addition to the four Maxwell's equations for the electric and magnetic fields, we need to remember the Lorentz force equation, which tells us how to calculate the force on an electric charge Q due to the electric field E and the magnetic field B. A magnetic force is only exerted if the charge is moving with a velocity v. So let's set up an experiment in the reference frame of a room or a lab that we're standing in. Let's say that we have a wire full of positive and negative charges arranged in a line that extends far in both directions to the left and the right. Because the positive and negative charges are balanced, they cancel out, and there is no net charge. By the first Maxwell equation, since there is no net charge density that's either positive or negative, there is no net electric field. However, let's say that the negative charges are traveling to the right. By the fourth Maxwell equation, since we have a current density J, a magnetic field will be created curling around the current. So we can see that this B field is curling around the line of moving charge. Now let's imagine that we have a nearby single lone proton that's traveling to the right. And let's say that this lone proton is traveling at the same speed as the negative charges. Now let's consider how the Lorentz force acts on this lone proton. Again, since there is no net charge in the wire, there is no electric field, so the Lorentz force has zero electric field portion. However, there is a magnetic field B. And at the position of the lone proton, the magnetic field vector points outward out of the computer screen. Now, if we do the cross product between the right-facing velocity vector v and the outward-facing magnetic field vector b, we end up with a downward-facing force vector f by the right-hand rule. So in the reference frame of the room or the lab, the Lorentz force pushes the lone proton downward, specifically through magnetic forces, and so the lone proton will follow a path like this. Now let's look at the same situation in the frame of reference of the lone proton. The lone proton is now stationary with a velocity of 0. Since the negative charges in the wire have the same velocity as the lone proton, they are also stationary in this frame. However, the protons and the room itself are now traveling to the left. Again, according to the fourth Maxwell equation, a current of charge results in a magnetic field curling around it. Now, since this line of charge is traveling in the opposite direction, but also has opposite charge, positive instead of negative, we get the same magnetic field as before. When calculating the Lorentz force on the lone proton, there is once again no electric force because the positive and negative charges in the wire cancel out, and there's no net electric field. But in this case, there is also no magnetic force. Even though there is a magnetic field, the lone proton now has a velocity of 0, so this cross product between the velocity vector and the magnetic field vector goes to 0. So we found that in the frame of the room, the lone proton experiences a downward Lorentz force and is pushed away from the wire. However, in the frame of the lone proton itself, the proton experiences no Lorentz force and is not pushed away. What we've discovered here is that the Lorentz force is not invariant under the Galilean transform, which is our standard method for changing reference frames just by adding or subtracting velocities. The Lorentz force exists in one frame of reference, but not another. If we assume that Maxwell's equations are correct, this means that there's something wrong with the Galilean transform. Now, this probably won't make too much sense now, but the solution to this problem is to replace the Galilean transform with something called the Lorentz transform. The Lorentz transform results in length contraction, which says that moving objects will contract in size. Since the positive charges are moving in the reference frame of the lone proton, they undergo length contraction and get closer together. And because the negative charges were already moving in the frame of the room, they were already undergoing length contraction. And in the frame of the lone proton, they will spread out since length contraction is no longer happening. Notice that if we take this length contraction effect into account, the positive charges are now more densely packed than the negative charges. This excess of positive charge creates an electric field which points away from the wire. The lone proton now experiences a Lorentz force that's due to the electric field, which pushes it downward. So we can see that when we change reference frames using the Lorentz transform, in the frame of the room, the lone proton gets pushed away because of the magnetic Lorentz force. But in the frame of the proton itself, the proton is pushed away because of an electric Lorentz force. The Lorentz force is invariant and equal in both reference frames. It's just that in one frame, the force is due to the magnetic field, and in another frame, it's due to the electric field. So we can see that using the Lorentz transform instead of the Galilean transform fixes the invariance problem with Galilean relativity. But you might still be wondering why length contraction happens at all. It will take me another few videos to fully explain this, but I'll start by saying that length contraction is a result of considering the speed of light to be invariant in all reference frames. I'll show you why this is the case. Let's again look at the four Maxwell's equations, which use the operations of gradient, divergence, and curl from vector calculus. Now, let's start by assuming that we're in a vacuum. This means that we remove the sources of electricity and magnetism. We'll set the electric charge density ρ to 0, and set the electric current density vector j to 0 as well. So we have the four Maxwell equations in a vacuum. And next we're going to make use of this special vector identity here. It says that the curl of some vector field v is equal to the gradient of the divergence minus the divergence of the gradient. I'm not going to bother proving this. It can be proven if you plug all these formulas into the identity, but it's pretty painful. So you can either look up a proof or try it yourself. Now let's start with the equation for the curl of the electric field. We'll take the curl of both sides. On the left, we'll replace the curl of E with the gradient of the divergence minus the divergence of the gradient, using this identity we talked about. On the right side, I've switched the order of the time derivative and the curl. This is allowed because the curl just takes derivatives with respect to space, and the order of space and time derivatives shouldn't matter. Next, because we're in a vacuum, the divergence of the electric field is 0, so we can set this to 0. We can also rewrite the divergence of the gradient using this operator, which is called the Laplacian. Also, the curl of the B field is equal to this, so we can substitute this into the equation. After cancelling out the negative signs and bringing the physical constants out in front, we get these equations. So we have the second derivative with respect to space on the left, which is the Laplacian operator, and we have the second derivative with respect to time on the right. This means that we have a wave equation for the electric field. This resembles other similar wave equations for vibrations in the air and vibrations along a string. And if we go through this process again, starting with the curl of the B field, we end up with a similar wave equation for the magnetic field. So we have derived wave equations for both electric and magnetic fields. And in a wave equation, the speed of the wave is located in this c coefficient here. This means that the speed of electromagnetic waves is equal to 1 divided by the square root of this product. Mu naught is the magnetic permeability of the vacuum, and epsilon naught is the electric permittivity of the vacuum. These are well-known physical constants, and when we plug them in and churn through the math, we get that the speed of an electromagnetic wave is about 3 × 10⁸ meters per second. I've left out the units in these physical constants to save some space, but if you search them online, you can check that the units correctly work out to a speed in meters per second. So we found that when we take Maxwell's equations, which are laws of physics, and study them in a vacuum, we can calculate the speed of light, which is an electromagnetic wave. This seems to indicate that the speed of light is a law of physics as well, and that it's possibly true in all reference frames. So this is strong theoretical evidence that the speed of light is the same in all inertial reference frames. But in physics, theory doesn't mean anything unless it agrees with real-life experiments. In the late 1800s, many physicists believed that light traveled in a special fluid called the ether, which was a special reference frame that was absolutely stationary. Given this idea of the stationary ether fluid, the Michelson-Morley experiment had the goal of measuring the speed of the Earth as it traveled around the Sun through the ether. They attempted to measure the speed of the Earth through the ether by measuring the difference in the speed of 2 light beams in perpendicular directions. If the speed of light was slower in one of these directions, this would give information about how fast the Earth was traveling through the stationary ether. This experiment was done by splitting a beam of light into 2 using a beam splitter, and then using mirrors to join the beams together again. The interference pattern of light waves at the detector would describe the difference in the speeds of the light beams. However, the result of this experiment was that there was no difference in the speed of light in both perpendicular directions. This provided strong experimental evidence that the speed of light is constant in all inertial reference frames. And this sets the stage for Einstein's special relativity, assuming that the laws of physics are the same in all inertial reference frames, and assuming that the speed of light c in a vacuum is also an invariant law that's the same in all inertial reference frames. We're going to find that this simple change has dramatic consequences for physics. In Galilean relativity, we found that different inertial frames all agree on time, but disagree on position. Using the position, it's relatively easy to calculate velocity, acceleration, momentum, and kinetic energy. We also found that velocities add together using simple addition, and that the laws of motion work in all inertial reference frames. When we move to special relativity and assume a constant speed of light, most of this will no longer be true. We're going to find that different inertial frames will disagree on the passage of time because of an effect called time dilation. Quantities like velocity and acceleration will be more difficult to measure because since different reference frames disagree on time, they will also disagree on how to take derivatives with respect to time. We'll find that velocities can no longer be added together using simple addition because there is a maximum speed of light, which is c. And the laws of motion, such as Newton's second law and Newton's law of gravity, are going to need some rethinking. Despite all of these dramatic sounding changes, the mathematics of special relativity is not that different from the mathematics of Galilean relativity. We can do the physics in the exact same way. All we do is replace the Galilean transform matrix with the Lorentz transform matrix. We will see in the next video how using the Lorentz transform matrix to change reference frames will impact the physics that we observe. Also, I realize these past few weeks have been hard on a lot of people, both because of the pandemic, but also because of the police brutality going on in the United States and other countries. If you like my videos and have the ability to do so, I'd encourage you to donate some money to charity. If you live in either Canada or the United States, I've left some links in the description where you can donate to your local food bank, or donate to the families of the victims of police brutality, or other charities as well. If you live in another country, maybe consider searching online for a charity closer to your home and sending them some money.